What I'm going to present to you here is just a couple of questions on proof by induction. What I want you to do is read the questions, pause the video, have a go at them, and then come back and check your answers with what I'm going to present to you. So, here you go. So there you go, as promised, 2 questions, both on proof by induction. I want you to prove both of these conjectures using the technique that we've already described. So, pause the video and have a crack at that. So the first one, I want to prove that n cubed plus 2n is divisible by 3 for all n, where n is greater than or equal to 1, and n belongs to the natural set of numbers. So first thing I have to do, if you'll remember, is prove it for a set value. And in this case, what I'm going to do is prove it for n equals 1. The first value in the set of numbers it's valid for. So if I show for n equals 1, what I get is 1 cubed plus 2 times 1, which equals 3, which is in the 3 times table, so therefore it's divisible by 3. Remember, for anything to be divisible by 3, it has to take the format of 3k. If it takes that format there, then we're laughing. So if it's divisible by 3 here, this one's 3 times 1, we're laughing. So we know it works for the lowest value in a set. Second thing we do is then assume it's true for a generic value n equal to k. So what that then implies is that k cubed plus 2k is some format of 3 times a. So it takes that format there. So it's divisible by 3 somehow. If I then look at n equals k plus 1, what that then means is that I've got k plus 1 cubed plus 2 times k plus 1. Now if I expand this set of brackets here at the start, what I'll get is I'll get k cubed plus 3k squared plus 3k plus 1, and then I'll have this second bit here, which is going to be plus 2k plus 2. So what I can now do is simplify all of this. What I'll end up getting is k cubed plus 3k squared. I'm then going to simplify the k's and get plus 5k, then plus 3. Now I know that doesn't look divisible by 3 at first sight because of this 5k. However, what I'm going to do is split this 5k up, and I'm going to write it as k cubed plus 2k plus 3k cubed plus 3k plus 3. Now the reason I'm doing this is this part here, k cubed plus 2k, takes the exact same format as this, the n cubed plus 2n, but for a value k. And we also know that from our assumption here, that k cubed plus 2k is equal to 3 times some value, so 3a. That means that this here is 3 times something a. So it's in the 3 times table, it's divisible by 3. This here can have plus 3 times k cubed plus k plus 1. Now I don't have to worry about factorising that because if I multiply 3 by it, it's divisible by 3. So essentially I've got 3 times something plus 3 times something, which if I take a common factor of 3 is going to give me 3 times, well, something that combines a and b, so let's call that big X. So because it's 3 times something, it's divisible by 3. So what I've done is I've shown it holds for the first value, I've assumed it's true for a generic one, which then leads me to show it's true for the next value. So what I can then say is therefore, since it's true, for n equals 1, n equals k and n equals k plus 1, that has the implication that it's true for all n which belong to this set of natural numbers. So we've just followed the same steps as we normally would with our proof by induction. First, assume, show for the next, communicate our solution. Now the second question was I wanted to show that the sum from r equals 1 to n of 3r plus 1 is the equivalent of a half n bracket 3n plus 5 for all integers where n is greater than or equal to 1. Now just because it's got a sum involved doesn't mean any of our steps change, they still follow the exact same pattern. So we still start by doing the exact same thing. So we take n equal to 1, and what we do is we look at both sides and see what we get. So the sum from r equals 1 to n, well this time it's r equals 1 to 1, so it's just that on its own, is 3 times 1 plus 1, that equals 4, so that's my left hand side there. My right hand side, which is here, I get a half times 1 bracket 3 times 1 plus 5, so that's the equivalent of a half times 8, which is equal to 4. So what I can say then is that it's true for n equal to 1. What I can now do is assume that it's true for n equal to k. So what that then means is that gives me the implication that the sum from r equals 1 to k of 3r plus 1 equals a half k bracket 3k plus 5. I'm then going to look at the next term. So I'm going to take n equal to k plus 1. Now what that means is that's the equivalent of doing the sum from r equals 1 to k plus 1 of 3r plus 1. Well, I can break this down and say that that's the same as doing the sum from r equals 1 to k of 3r plus 1, adding on the next term, which is when we've got k plus 1 for the r, which would then be plus 3 bracket k plus 1 plus 1. So that's just the format of the next term, the k plus 1th term. Now the reason I've split it up like that is that I know that this section here is given by this, because that's my assumption that it's true for n equal to k coming into play for this one. So I can substitute this here in for that. So I know then is that's the equivalent of a half k bracket 3k plus 5 plus this second bracket here, which gives me 3k plus 4. What I'm now going to do is try and simplify that, because if I can simplify this using this conjecture here and get it to a form where I've got a half bracket k plus 1 and then 3 times what would be the k plus 1 here, simplifying it would give me 3k plus 8. If I can somehow get this out of that, then I've shown that it's true. Well, to start with, I want to take a common factor of a half. So to do that, I'm going to have a half k bracket 3k plus 5. I'm going to write this second bracket as plus a half bracket 6k plus 8. Take out a half as a common factor, and what I'm then going to do as well is multiply this first bracket out, and I'll get 3k squared plus 5k plus 6k plus 8. I'm then going to have a half. If I simplify this bracket here, I get 3k squared plus 11k plus 8. And what I now have to do is factorise that. If I can factorise it and get it into this form here, then I'm laughing. Well, funnily enough, 3k squared plus 11k plus 8 simplifies down to a half, bracket 3k plus 8, k plus 1, which is exactly what I had here. So then it holds for the k plus 1th term. So then I can say my induction, which means therefore that implies that since it's true for n equal to 1, n equal to k, and n equal to k plus 1, the implication from this is that it's true for all n where n is greater than or equal to 1 and it's the integer values. So I've proven the statement was true. I've worked it through following those same 3 steps that we talked about a moment ago and induced that my final answer means that my overall statement is true. So I've stuck with my guns, done first term, assumed it's true for the kth term, shown it's true for the next term, and then communicated my solution. Proof by induction is straightforward when you get in the habit of following those steps. It may require a bit of jiggery-pokery, a bit of algebra, and looking back at bits that you've done previously in this question, or things that you can assume from other areas, i.e. Pythagoras, that sort of thing. But once you nail that and those 3 steps, proof by induction shouldn't cause you any major issues besides a few algebra headaches.